Okay, we're ready for our final presentation of the evening. Presentation 3 is a mechanical engineering presentation. It's entitled Hoyt HVAC, that's heating, ventilating, and air conditioning design project. The advisor is Dr. Vern Ulrich. Please begin your presentation. Folks, I'm not hearing your presentation.
Sorry about that.
Okay, why don't you do a restart on that? Thank you.
Okay. Hello, everyone, and welcome. My name is Brody Rogers, and together with our advisor, Dr. Ulrich, team leader, Ashton Petroboni, Katie Knechtel, Ian Yoder, Alexandra Eicher, and Austin Wacker, we are the Hoyt Hall HVAC project team. The basic scope of our project was to design an HVAC system for Hoyt Hall to allow for air conditioning and better control of heating. We wanted to design around the current existing conditions to allow for minimal building alteration, as well as update the current systems for better control. In order to do this, we first started with a survey, which Katie will talk about shortly. Once we created the model, the ductwork, piping, and all other existing conditions could be drawn in as well. Last semester, our main goal was to create the actual model of Hoyt in Revit. We were not focused on the fine details of the building, but rather learning the basics of Revit. The biggest help to making the model was completing the survey, as it allowed us to be able to see the spacing and layout of the building. The model itself took a majority of the time last semester. Setting it up so everyone could work on the model remotely was a very difficult challenge, and getting the family set up took a lot of teamwork and coordination. To speed up the process, however, we did use a lot of pre-made objects that Revit comes equipped with. As for this semester, we first wanted to update the model with objects that better represented Hoyt, such as creating the large arched windows in the center, as well as updating the windows and doors. We also needed to do the load calculations for heating and cooling to figure out zoning. Once we had the desired zones, we were able to pick which air units we would like to incorporate into our system. The load calculation also aids in the sizing of the ducts. Once the ducts were determined, the ductwork could be drawn in and the controls were picked. Lastly, we wanted to place the controls in the model and populate it with regular furniture, such as desks, tables, chairs, and things of that nature. Now here's Katie to talk about surveying.
As Brody said, last semester we primarily focused on surveying Hoyt and building our model. The original blueprints that we got from the college were from the 1960s, so they were out of date, as there had been a lot of old labs that had been turned into offices and bathrooms had been added on both floors. So our objective was to compare these drawings to the conditions we found in Hoyt. Our survey included taking dimensions of each room, including the ceiling height and how much space there was between the ceiling and the next floor, so that we knew how much room we had for ducts. We also looked at different walls and window and door types, so we knew what we should put in the model. As well, we determined where the utilities entered and left the building and where they were located, so we knew what we had to work around when adding our duct. All of the surveying enabled us to compare the notes that we took to the blueprints, and we used those drawings and converted them into AutoCAD drawings. AutoCAD is a computer-aided drafting software that enabled us to draw updated versions of the floor plan easily. AutoCAD is nice since it allows us to import the plans into Revit and use them as a background, which we started to draw on. Another benefit is that it allows us to make a plan that we are able to make consistent for each of the floors. This semester, we had very limited use of AutoCAD. We used it as a skeleton model for routing the ductwork in Revit. This made it easier for us to follow the paths of the duct mains when we were inputting the ductwork into the Hoyt Revit model. To do this, we printed out last semester's AutoCAD floor plans and we made 3 sets of them. We used one set for mechanical drawings, one set for the plumbing, and one set for all the controls that we added. We did this so that we could mark up all of the plans as a sub-team by hand and then reconvened to make sure that there would be no interferences with pipes and ducts when we went into model them in Revit. We also wanted to map out the most direct and efficient way to put the components in the building before we actually inserted them in the model and realized we had to change them later. These were then inputted into the AutoCAD floor plans, which were linked into the Revit model. The pictures in the top right corner are the mechanical floor plans for each of the 3 floors. These are the printed versions that we drew on by hand, and they're a little small, but that you can kind of see that they're very cluttered and messy. You can see the cleaner version in the lower left corner that we created in AutoCAD by drawing the work into the floor plans. Up next, Ian will talk about train trace.
Okay, so this was the first step taken this semester in designing the Hoyt HVAC system. This process was extensive, as this is where the calculations took place that would give us the data and the numbers that would drive our designing process for the rest of the project. It was imperative to make sure that these numbers were correct and accurate. Each room of Hoyt was individually placed into the train trace load calculation system, and the necessary trace for each room were specified. These traces will be discussed on the next slide. All in all, there were 56 individual rooms set up. However, some of these 56 were hallways, atriums, and stairwells. The specifications that were needed for each room were as follows. Area. This is literally just the floor area of the room. It was found using AutoCAD's area function. Maximum occupancy. This is either the largest number of people a room can hold. For a classroom, it would be the number of available seats, or it is a high average of people that would be found in the room during the day. For the machine shop, for example, this number fluctuates. This was found by either counting seats using ASHRAE tables based on area. Lighting wattages. This is the amount of heat that lights would give off in this typical room. This is also found using ASHRAE tables. Additional heat loads. This includes the heat given off from the computers, printers, projectors, etc. And this is also found on ASHRAE tables. Area of exterior walls. Found by multiplying the length of the exterior wall by the height of the exterior wall. Direction which the exterior wall faces. This is the input as a number in degrees, with north being 0, east being 90, south being 180, and west being 270. This is important because the sun has different hours of exposure to the walls based on which direction they are facing. Area of the glass exposed to sunlight. This is found by calculating the area of the window on the exterior walls. Area of the exterior doors. This is found by calculating the area of the door on the exterior walls. Ceiling height. This is found by measuring the floor to ceiling height. Floor height above ground level. For the first floor, it is just counted as a slab on grade, assuming there is no basement, and for second floor, it is the distance off of the ground. Partitions surrounding the room. This is not majorly important for most of our rooms. However, for the rooms where there are large heat loads next to them, like the machine shop, for example, you specify what room is next to it and is putting off excess heat. Typical use of the room. This is a drop-down menu in train trace, based on ASHRAE standards. This would include the type of activity that goes on in the specific room, that be it a classroom, lab room, office, storage, etc. Here's an example of the inputs in train trace for a room in Hoyt Hall. In the figure on the left, you can see just an overview of classroom 113. This included a brief summary of all the inputs. The figure on the right shows the specific room inputs, such as the room area and ceiling height. In the figure on the left here, you can see the U factor for the ceiling and the type of ceiling. In the figure on the right, you can see the exterior wall information. There is a north, east, and west exterior wall in this classroom. You can also see the window type and area specified here. In the first image here, you can see the internal loads such as people and miscellaneous loads. In the right clip, you can see the airflow specified and the room usage criteria. In this image, you can see the partitions tab. There were no partitions for this room, but here you can see the slab on grade option selected for the floor. Once this process was completed, for all 56 individual spaces, the rooms were assigned to a unit in the software. The units we ended up selecting were packaged air handling units mounted on a slab on grade outside of the building. We arrived at this unit type for several reasons. The first was cosmetic. Hoyt is essentially a located building on campus. It is easier to build a fence and hide a single piece of equipment as opposed to have to hide air handlers and condensers if we did a split system. This makes the package system more favorable. Secondly, we chose these package units mounted as a slab on grade for functional reasons. It would not be feasible to mount any units on the roof, as the roof of Hoyt is sloped, and we would need to reconfigure the structure of the roof to make flat spaces to place the units on. We also do not have the same setup that is on HAL, where the units are actually hidden between the slopes of the roof on the top of the building. This is what the system output looks like once you assign the rooms to a system. There are several key numbers to look at on these sheets. The first two are just checks to make sure that you set the space up correctly. The floor and the roof areas must be equal, unless you have a walkout section that is being conditioned. However, we do not. The second is the people load must be reasonable. If you base the number of people off of area in the ASHRAE tables, every so often you will get a grossly overestimated number of occupants. If these two numbers are satisfactory, then you can look at the total tonnage of the room or the unit in the bottom left corner of the sheet. Each room has a specific tonnage. These rooms are added up and placed into zones. These zones determine the size of the unit you require. In our case, we needed a total of 70 tons of cooling divided up amongst 3 units for our 3 zones. For each unit, you can now size the ductwork coming from it and supplying the rooms using the following equation. Tonnage times 400 CFM per ton is equal to the nominal CFM per unit. Using the available CFM, a ductulator is now able to be used to help size the appropriate sections of ductwork coming from the unit into the room based on a 0.1 inch water column loss per 100 feet of duct. Finally, there are some things to note. 70 tons is exceptionally massive for a building the size of Hoyt. This number is so large based on the minimal insulation effects Hoyt's structure offers. The windows and doors are not insulated at all, and the exterior walls are all masonry. In order for this number to drop down to a reasonable and economically justifiable scenario, insulation would have to be added to reduce the loss of energy from the building. This would also reduce the size of the units, making them smaller and easier to hide outside of the building. Now I'm going to have Ashton talk about the Revit model and some existing conditions in Hoyt.
Thanks, Ian. So here you can see one of the main points of our project, which is our actual model. And this is a great thing that we can use in Revit to actually show off what we've done, as opposed to just having results on paper and numbers that to the average person really don't mean much. So here you can see this is a render of the outside of our model. It shows the custom windows that Brody mentioned earlier, as well as our units that we added in at various points around the model. So in order to do the ductwork, we first had to put in the reflected ceiling plans, or the RCPs for short. These are very useful because you can set up how the ceiling tiles are actually laid out in a room and space the diffusers out to have a more accurate depiction of the room layout. These ceiling plans were put at the current height of the ceiling in the room, but there are a few that had to be dropped in order to accommodate some of the ductwork, namely the 3D printing room and the junior and the senior laboratories. Placing the ductwork is very simple. You select the shape of round, rectangular, or oval, and then set up the sizing you need. Typing in an elevation should set it at that elevation, and lastly, clicking the start and end points. The fittings are a little trickier, but they're still relatively easy once the families are set up correctly. As for the plumbing, it's very similar, and in some ways easier than the ductwork, because you don't actually have to pick any shapes. All piping is circular. So along with the plumbing, we also put in the water closets, urinals, and the lavatories to resemble what Hoyt actually would look like. After all the ducts and plumbing were run, we connected the ducts to the 3 air conditioning units that we placed around the model. The last thing we did was populated the rooms with typical office and classroom objects. Similarly to the preset windows and doors that Revit has in their database, they have a large amount of preset furniture and other objects to put in your model. We did modify these objects a little bit to better represent existing conditions in Hoyt. When a consulting firm is presenting the model to the customer for final approval, these objects are used to fill the space and give the client a better idea of what the finished product will look like using walkthroughs or flybys. This does require rather large computing power, which we don't have available to us on our laptops, so we weren't able to do this for you guys. So what systems already exist in Hoyt? Well, let's go through and start at the basics. We have a basic steam heat system that is already existing. The problem with this system is it's either always on or always off, because a lot of the thermostat and the valving has kind of gone bad on it, and it doesn't really work that well anymore. If anyone's taken a class in Hoyt, or anyone's taught in Hoyt, or has their office in Hoyt, you guys know that it can get pretty unbearable in there. Along with this, in the pneumatic thermostats, there's no automatic valving. They're all hand valves that you would have to go and turn. So if you want to isolate it, part of the system, you have to go find where the valve is and turn it off yourself. So our system will be reusing this existing system. There is also no air recirculation in Hoyt, which is unfortunate because the buildings in the 50s were designed to kind of have the windows open to recirculate the air. So we're going to be reusing all of the existing piping, which is very nice. It really helps out our design. And we are going to be reusing the domestic cold water, which serves the laboratories, water closets, and the urinals on the bathrooms. and as well as the water fountains in the hallways. The domestic hot water, which serves the lavatories and the sinks only. The sanitary system, which is drainage for the water closets and the urinals in the laboratories. And the passive steam heat, which is the radiator system that's on the outside walls of Hoyt. So our HVAC system will take a lot of the problems that the current system has and remedy them. So one of the things we wanted to address was the issue of having 100% heat on or off. So we would suggest putting in automatic valving that would allow you to modify this amount of heat to call for whatever a thermostat's set to. So our system will also bring something new to Hoyt that is much welcomed, which would be air conditioning. If anyone knows and you've taken a class, it's very hot at the beginning and the end of the year, and that's because there's no air conditioning in Hoyt. You have to open the windows to get any airflow, which is kind of atrocious on days when it's raining because the building becomes extremely humid. And you also have to shut the classroom doors, which really ruins the airflow in the building. So based on our design, a central ventilation system which would be added, which would give the air conditioning to each room and also allow us to distribute heat that can kind of pocket in the building, as well as having closed windows and closed doors to allow for a quiet classroom and air circulation at the same time, giving Hoyt its much needed air movement. So I'm going to pass to Alexandra, and she is going to talk about the
controls and zoning. Hello, everyone. Hope you're having a nice evening. Let's dive in with the basics of air handling units. From the exterior, HVAC systems seem fairly straightforward. They consist of long channels of ductwork that allow for air to flow throughout a building. If we turn our attention to the schematic, it is clear that there are many detailed components at work in the air handling unit. Starting at the bottom left, the system takes in outside air and passes it through a sequence of dampers, valves, and air filters before it reaches the cooling coil. Once the air reaches the desired conditions, a supply fan drives it into the zone. A zone being a single conditioned space controlled by a single thermostat. Ordinarily, there are 3 temperature sensors in a single system, at the inlet, at the cooling coil, and the thermostat itself. To make way for fresh air, air in the zone is returned to the air handling unit. Depending on the requirements for the zone, a portion of the returned air can be recirculated and mixed with fresh air. This increases our system's efficiency because that returned air is already at the required conditions. If it cannot be recirculated, the air is exhausted. Moving on to controls. Controls are required for monitoring system performance, reducing energy use, identifying maintenance problems, maintaining thermal conditions, and optimizing indoor air quality. The 3 main controls implemented in an HVAC system are thermostats, humidistats, and aerostats, which maintain temperature, humidity, and room pressure, respectively. These controls are set to maintain the air conditions within a certain range of values. They send correcting signals to the air handling unit when the air quality is not held to those desired values. For overall thermal comfort, ASHRAE suggests that in the winter, room temperature is held between 68 and 75 degrees Fahrenheit and 73 to 79 degrees Fahrenheit in the summer. The relative humidity in a zone should be between 25 and 60%. The ASHRAE pressure recommendations are to maintain positive room pressure between 0.01 and 0.05 inches water column. This slide features the controls we selected for our system. We looked at our building's requirements in terms of size, humidity range, pressure requirements, and desired temperature range. Our contacts at Siemens were very helpful in the selection process. As you can see, these controls monitor the entire building. We do not have time to go through every control we selected, however. We will focus on these 4. The 533-3768 control is an averaging rigid temperature sensor, which is mounted inside the duct, 1 per each zone. This control monitors the air temperature in a duct and communicates that information back to the air handling unit. The PXC modular provides superior flexibility for monitoring temperatures and makes it an optimal solution for handling unit control. It also helps communicate between different fire protection systems. The QFA3160 is a Q-series outdoor control that monitors the air conditions, critical environment, relative humidity, and temperature. It is located outside of the system and provides external data. The QP series, FWSC2, communicates with room sensors for use with Siemens terminal equipment controllers, otherwise known as room sensors. These controls are required throughout the system, one in every room. Moving on to zoning. Initially, we had wanted to implement a 6-zone system, dividing our building up into the fishbowl lab, machine shop, 3D print shop, restrooms, and offices. After doing some train trace calculations, we determined that a 3-zone system would function best for the building. This system requires 70 tons of cooling, which is divided up into a 35-ton, 20-ton, and 15-ton unit. The 35-ton unit feeds to the lab zone, shown in blue. The 20-ton unit feeds to the office and lobby zone, shown in green. And lastly, the 15-ton unit feeds to the classroom zone, shown in red. These 3 zones serve the entire building. The 3rd floor is served entirely by the lab zone. The classrooms being on their own zone allows for us to turn it off and save energy during off hours. As is visible, our system does not control the attic space because the attic is largely unused. Now I'm going to pass it off to Austin, who's going to discuss our financial report.
Thank you. Due to the computer-based nature of our project, an engineering economy analysis does not provide much insight. As a whole, the project involved only 3 costs, those being 8 3D printed models of Hoyt Hall, the train trace software, and 9 AutoCAD floor plans from the GCC print shop. The most significant cost was the 3D printed models at $12 each, for a total of $96. These models will help promote senior design projects and the engineering department at GCC as a whole. The train trace program at $60 for 10 licenses was a key part in finding the cooling loads and the overall tonnage of the system. Further, the AutoCAD prints from the GCC print shop included 3 sets of the 3 floors of the building. In total, these cost $36. These prints were a key part in finding the best layout of the systems in the ceilings of the systems in each ceiling for every floor. The nature of the project allowed for minimal expenses while producing a very high quality result. Cost was in no way a restriction in finishing the project. Each cost played a key role in the success of the project, and without each one, the project would not have been finished in the way it was. This diagram shows the percentage cost of each of the 3 expenses. As I mentioned earlier, the 3D models accounted for the biggest piece of the project at 50%. With that, a 10% increase in the cost of the 3D models would result in a 5% change in the total cost of the project. Each of the 3 expenses exceeded 10% of the total cost. Therefore, any change in any of the 3 expenses would result in a significant change in the total cost. This chart shows cumulative total cost of the 3 expenses. Together, the 3D models and the train trace program accounted for 81% of the total cost. This means that a 10% increase in them would result in an 8.1% increase in the total cost of the project. Due to the computer-based nature of our project, the overall cost was only $192 with those 3 expenses that I described earlier. Thank you for your time. Are there any questions?
Any questions at this time?
Hey guys, I'll jump in with the first question. Appreciate the presentation. I had a question for you about air changes. You know, you talked quite a bit about heat loads, but not too much about air change requirements. Could you just comment on that, in particular, how the air change requirements are different among the three loads I would expect?
Yeah, I can answer that if you guys can hear me. So in the train trace program, we actually just set all the air requirements to ASHRAE minimums because we weren't sure what each space really counted as. So those were just set to the ASHRAE minimum air changes per hour. Obviously, lab rooms and then like places like the 3D print room would require more, but the 3D print room is actually on its own system right now, so we kind of left that out of our own calculations.
What is the ASHRAE minimum? I don't remember. Is it 4 or
I don't
3?
know what the ASHRAE, it's just an option. We used ASHRAE 62.1 in the train trace software, so we just selected just the ASHRAE minimum based on that zone.
Okay. How do you think that any changes to that might affect the equipment? You know, for example, I know, you know, for a typical office space, you might have 4 air changes per hour. A classroom, you might want more like 10 to 12 or even 15. For a machine shop, I imagine it'd be quite a lot higher.
Yeah.
How might that affect your design?
Well, obviously the equipment size would go up because we'd be required to have more exhaust air. We have a plenum return right now, so it wouldn't affect any of the return air per se, but it would affect more supply air being required, which would then obviously upsize the units outside the building. So.
Oh, sorry, I missed that. You have a common plenum return for all 3 zones?
Yes.
Okay. Are you concerned with mixing machine shop air with the rest of the building?
So I'll answer that if I can. Actually, believe it or not, the machine shop and the bathrooms are not allowed to have returns in them by ASHRAE standards. So we actually have them exhausted to the outside, or in the case of like the machine shop, we would have that air run through a filter if it needed it. But in this case, it can be exhausted directly to outside. That air cannot be returned through the plenum.
Okay, great. Thanks, guys.
Thank you. Any other questions?
When sizing the ductwork, was there a maximum velocity or maximum aspect ratio that you guys looked into doing? And if so, what were those numbers?
Again, I guess I can answer that. So the only restrictions we didn't have a set ratio. We just looked at ceiling height and like what our clearance was above the ceiling. In the first floor, we just made things as shallow as possible and as wide as possible because we don't have as much clearance there. In the second floor, we just kind of kept everything at least, 2 times as wide as it is tall. But most of our requirements were just making sure they fit in the ceiling space.
All right.
I had a question regarding the retrofitting of a building which doesn't have, forced air heat. Obviously, if it had forced air heat, it would be, not trivial, but it'd be a lot easier. In terms of your cost, is that your main cost, installing all those runs for the forced air versus the unit itself? I can't remember the breakdown, but I was just wondering if that's a major cost, because that would seem to be a pretty big deal.
So we didn't actually get a cost for our final project to do it with a bid because everything that went on, a lot of companies are kind of closed right now and wouldn't really offer bids. But the main part of our cost of our project would actually be the units, because they're more in the sense of you would order them in a custom fashion. They're not something that you can just get off the shelf at a store. So in the way of reusing our project, we actually saved ourselves a lot of money by putting in the new valving.
Okay, so you didn't really get a chance to look at the price then to put in the ductwork and all that?
Unfortunately not.
Okay. Thank you. Any other questions?
I might have missed this from earlier, but did you guys say what units, outdoor AHU units, you guys kind of based your design off of, or did you have like a basic model that you looked at for sizing?
Oh yeah, these are just, I think this answers your question. These are just typical Linux units. I got these off of the Linux website. We sized them using the train trace, and then I just sized them based on tonnage and BTU. I don't know if that answers your question, or.
I was just like, did you have like a specific number for it, or is this just a general model that you guys were putting together? Because I mean, I understand you can't always get the best numbers from contractors, or even any numbers from contractors, especially during this time. But I was just wanted to ask if there was any particular number to it, like 235-ton units, 170-ton.
Oh yeah, so we did split them up. I think Alexandra talked about that maybe in her section. We have 3 units, 70 tons total. So it's 35 tons serving zone 1, 25 tons serving the other, and then 20 in the other, or 15 in the other, I think it is. Alexandra, do you have the exact numbers on that one?
Yes, I do. It was split up into 35, 20, and 15.
Okay.
We have time for one final question.
I just want to chime in and make a comment. This is Dr. Yu. You guys did a great job.
Thank you, Dr. Yu.
Okay, seeing that there's no further questions, congratulations to this team and all the teams. This concludes our session.